So we're going to continue now with section 5.2, eigenvalues and eigenvectors. And we're going to do another 2x2 matrix, find all the eigenvalues, and for each eigenvalue, we're going to find the set of eigenvectors that goes with it, the eigenspace that goes with it. So to find all the eigenvalues, we know we have to compute the characteristic polynomial. This is a 2x2 matrix. The characteristic polynomial is going to be a degree 2 polynomial. We're going to take the determinant of a minus lambda times the identity. That's a, and of course the 2x2 identity is 1, 0, 0, 1, and so lambda times the identity is lambda, 0, 0, lambda. And we'll just do this all in one step. So the determinant of a, so we'll subtract off lambda from each of the diagonal elements. From the off diagonal elements, we won't do anything at all. So 2 minus lambda, 1, negative 1, and then 4 minus lambda. And we're going to take the determinant of that. So this times this minus this times this, 2 minus lambda, 4 minus lambda, minus 1 times negative 1. Let's simplify a little bit. Lambda times lambda is lambda squared. Then we end up with a minus 2 lambda and a minus 4 lambda. That's minus 6 lambda. 2 times 4 is 8. Minus times minus is plus, so 8 plus 1 is 9. And we're going to take the determinant of a minus lambda times the identity. We're going to take the characteristic polynomial and set it equal to 0 and solve. Let's go ahead and factor this. This one factors nicely, but if it didn't factor, you could fall back on the quadratic formula. So we're looking for two numbers that multiply to give you 9 and add to give you minus 6, minus 3. And so this particular matrix has only one eigenvalue. Lambda equals 3. So let's go ahead and find the eigenspace that goes along with lambda equals 3. So we're going to take a minus lambda times the identity. So we'll take this and subtract off this lambda, 3, from both diagonal elements, and leave these off diagonal elements the same. So we're going to take a minus 3 times the identity and see what vectors that takes to the 0 vector. So a minus 3 times the identity. So 2 minus 3 is negative 1. We're going to leave that alone because it's off diagonal. We'll leave that alone because it's off diagonal. 4 minus 3 is 1. And we're setting it equal to 0. We'll write this as an augmented matrix. So 0, 0. That's the easiest way to work. Row operation, you do two row operations there. You take the first row, subtract off the second row. That gives you a row of zeros. And then I'll multiply the first row by negative 1. And that gives me this in reduced echelon form, which is 1, negative 1, 0, 0, 0, 0. So there's the same matrix in reduced echelon form. Well, this says x1 minus x2 equals 0. The second row doesn't give us anything. And so, in other words, it says x1 equals x2, and x2 is free. Let's go ahead and write this parametrically. So we're going to give each of our free variables a parameter. I'll call that t. So x2 is t, and since x1 is the same as x2, that's also t. So that tells us that x1, x2 is tt, which I can just go ahead and write t times 1, 1. So the eigenspace for lambda equals 3 is just the span of 1, 1. If you take a look at the example we did last time in class, we had two eigenvalues. I think each one had an eigenspace that was one-dimensional. So if you take the one-dimensional eigenspace for one, the one-dimensional eigenspace for the other, put them together, that's 2 dimensions. That was the size of the matrix, 2 by 2. And so that one, the R2 had a basis that was made up of just eigenvectors for the different eigenvalues. This one doesn't. This one has only one eigenvalue, and its eigenspace is one-dimensional. It's possible to have just one eigenvalue and the eigenspace is two-dimensional. For instance, if I take the identity matrix, it's easy to read the eigenvalues off of that because it's diagonal. The eigenvalue is, there's only one eigenvalue and it's 1, but the eigenspace is still two-dimensional. So this one and the one we did in class, they have a basis for the space that was two-dimensional, same size as the matrix operates on, R2. This one doesn't. That's going to come in handy, that distinction is going to come in handy in the next section when we try to distinguish what's called a diagonalizable matrix from a not diagonalizable matrix. That will put off to the next section. But I do want to mention a couple more things that have to do with section 5.2. So there is yet another addition to the invertible matrix theorem. So remember, the invertible matrix theorem gives you a whole bunch of equivalent qualities of a matrix which is invertible. So here's another one. So this is just part of the invertible matrix theorem that we haven't talked about yet. An n by n matrix A is invertible if and only if 0 is not an eigenvalue for A. If 0 is an eigenvalue for A, that means there is some vector such that A times the vector is 0 times the vector. Well, 0 times the vector is just the 0 vector. And you know that a matrix is not invertible if and only if it sends some non-zero vector to the 0 vector. So the proof of this is pretty obvious. So that's one thing I wanted to mention. Another thing that I wanted to mention is what it means for two square matrices to be similar. So if A and B are both n by n matrices, we say A is similar to B if there exists an invertible n by n matrix such that I'm going to get this in the same order that your book gives it to you. They say that A equals PBP inverse, such that A equals PBP inverse. So, for one thing, if A is similar to B, then B is similar to A. So we have an invertible matrix. Oh, P is the invertible matrix, such that A equals PBP inverse. We could have gone the other way around. If I multiply this both on the left by P and both on the right by P inverse, both on the left by P inverse and both on the right by P. So that gives me P inverse A P. I'll put the P inverse over here, and then the P B P inverse P. If you're wondering what I did, I just took this equation, multiplied both sides of the equation on the left by P inverse. There's what was there originally, and multiplied both sides on the right by P. Well, P times P inverse is just the identity. That goes away. P inverse times P is just the identity. And so I could have just as easily written B equals P inverse AP. So if we can get from B to A using one of these invertible matrices with its inverse on the other side, we can get from A to B doing the same thing. So that's what it means for two matrices to be similar. And as it turns out, if A and B are similar, they have the same characteristic polynomial. And so the same eigenvalues. So if they're similar, which is a very strong statement, they have the same characteristic polynomial. I do want to point something out. The converse of this statement is not true. So it's possible for two matrices to have the same characteristic polynomial without being similar. Here's an example. The identity matrix 1, 0, 0, 1 and this matrix 1, 1, 0, 1, these two have exactly the same characteristic polynomial. If we compute the characteristic polynomial for either of these, you will get lambda minus 1 times lambda minus 1. In other words, lambda squared minus 2 lambda plus 1. But these two matrices are definitely not similar. They're not similar. If I put a matrix and its inverse on either side, well then I'm just going to get the identity. The only matrix that the identity is similar to is itself. And it's definitely not similar to that. So it's possible to have the same characteristic polynomial without being similar. But if they are similar, then this weaker statement that they have the same characteristic polynomial and the same eigenvalues, that's true. That's it.